be executed. If it is executed in non-mutually exclusive manner, what output you will get. Okay, so that we saw. Now next, the related to race condition only, you should know what is critical section or critical region. Okay, what is critical section or critical region? Students, all of you can hear me clearly?
Yes, ma'am.
Okay. So what is critical region, or the critical region can also be called a critical section. Okay. So note down, the critical section is a code segment. Critical section is a code segment where the shared variables can be accessed. The critical section is a code region or code segment where shared variables can be accessed. Wherever the shared variables will be accessed, an atomic action is required in a critical region. What is atomic action? Only one process should execute the critical section at a time. Okay. Don't confuse. Technically, this sounds little hard, but in the previous example, in the race condition example, this is the shared, this is called the critical region. Okay. This is called a critical region. Why only this code segment is called a critical region? Because this code segment only will be executed by more than one number of processes. So this is a shareable code segment. More than one process will share this code segment. Okay. So now this segment is called a critical region. So whenever in a multi-processing system like this, the critical region is getting executed, only one process should execute the critical region at a time, then through which we can avoid the race condition. Through which we can avoid the race condition. It is very simple, students. See, here this example itself says, no, first when this process P1 is getting executed, no other process is what? Interfering in between. Okay. When P2 is getting executed, no other process is interfering the work of the P2. Okay. So when the execution happens in this way, then the race condition will not come. No. Whatever output we want, we expected, which is appropriate valid output, only that we will get. Okay. So that is called, this is called synchronization. This is called both the process P1, P2 are doing the inter-process communication in synchronized way, mutually exclusive way. Okay. So now here in the part in a synchronized IPC, inter-process communication, the code segment which is shareable by more than one number of processes is called critical region. Okay. What is critical region? The critical region or critical section is a code segment where the shared variables can be accessed. Here in a critical section, there will be atomic action is required. Why? What is atomic action? That means only one process can execute its critical region at the time. Now for process 1 also, this is a critical region. Process 2 also, this is a critical region. So process 1's critical region should, when it is executed, no other process should execute its critical region. For example, P2's critical region is also this. So when P1 is executing this critical region or being inside this critical region, P2 should not execute its critical section. Okay. So this is called a critical section. Very simple. To avoid the critical section, in the critical section, the synchronized way or mutually exclusive way the processes are communicated, then we can avoid the race condition. Okay. This is race condition and critical region. Okay. Now here they have given one example. This is there in your book. That's why I have given. Okay. Now there are two processes, process A and process B. Okay. Both the processes are started. That means now currently there are two processes in a multi-processing system. Okay. What are those processes? Process A and process B. Okay. Process A is executing here. Okay. So now these are called what? Here the process A did not access any shareable resource. It is using its own private resource. Okay. So same as here, process B till from here to here, it is using only its private resources. So it is not entering inside the critical section. Okay. So till this, there is no problem. Okay. Once the process A enters in a critical region, for example, here in this point, assume that, so to enter inside the critical region, there are many algorithms. Okay, we are just ignoring that here. We will see about the algorithm later. Okay, so process A is entering into the critical region here. This critical region is what? Shareable resource by process B also. Okay, so in they have given in T1 time, process A is entering inside its critical region. Okay. So now currently here and all the process A is in now in a critical region. Okay. It is in its critical region. Okay. But in the time T2, what happens? Process B should also, B also wants to enter inside the critical region. Okay. B attempts to enter critical region. Did not enter, attempt. It is trying. B attempts to enter inside the critical region. Where? In time T2. Okay. But in time T2, look at here, process A, still it is in its critical region. Okay. So the process B will be blocked. Process B will be blocked. Okay. So blocked means what? Process B should wait until the process A completes its execution being in a critical region. Okay. So process B should wait till process A come out from its critical region. Okay, in time T3, process A is coming out of its critical region. A leaves critical region. Okay, the moment A leaves critical region, already process B is waiting to enter inside the critical region. So it will execute some necessary algorithm and then it will immediately enter inside the critical region. Okay. Now here in this time period T3 to T4, that means T4 minus T3, who's there in the critical region? Only one process. Who's that? Process B is in the critical region. Okay. Now when it is coming out of the critical region, process B coming out of the critical region, process A, process B, that means the entire system is going to its starting state. How it was in a starting state, in the same state it is going. Okay, very simple diagram. What this the diagram says, at any point of time, T1, T2, T3, T4, at any point of time, if you look at the critical region, any one of the processes only there in the critical region. Okay, so T1 to T3, only process A is there in the critical region. T3 to T4, only process B is there in the critical region. After that, both the process executed its critical region. Okay, so it is coming out of the critical region. Now, both the processes are in non-critical region. Okay. So this is now I think you understood the critical region. Now, how we can implement this? Now, simply we said only one process should be there in the critical region. But using which logic you will implement this? So that is called the algorithm. Okay. So mutual exclusive algorithms. Okay. If you want to achieve, if you want to implement the mutual exclusion matlab what? Simply remember, mutual exclusion means mutually understanding. I said, example, only one eraser shared by two students. Both the students are mutually exclusive. Then they will use that eraser, that shareable resource in a synchronized way. There is no confusion. Okay. What is that mutual exclusion? There, when one person is drawing, another person should write. Okay, vice versa. So that is mutual exclusion. When mutual exclusion is there, what will not happen? That will not lead to race condition. So in critical region, always there will be a single process. So all these will be there. In our example, only one person, only one student at a time can use that eraser. Okay. So eraser, using eraser is what? Critical region. Okay. So that critical region can be executed by any one of the students at a time. Any one of the students at a time. Okay. There are many proposals of algorithms to implement the mutual exclusion. We will see what is busy waiting. Okay. It's a part to implement the mutual exclusion. Okay. So that we will see. Okay. Now all these algorithms are what? All these algorithms are proposal to achieve the mutual exclusion. All these are proposals to achieve the mutual exclusion. So all these algorithms are proposed. Okay. The first algorithm is called, it is not actually, we can't consider this as an algorithm, disabling interrupt. So through disabling interrupt, we can implement the mutual exclusion. See, now you are familiar with the word mutual exclusion, synchronization, interprocess communication, all those. Okay, critical region, race condition and all. So now whenever I'm using that term, you should be able to recollect what it is. Then only you will understand. Okay. Moreover, I'm recording this section. Okay. But anyway, I will ask the question. You have to listen also. Wait a second. Okay. Students, what is the disabling interrupt? Very simple solution for that is temporary solution, but this has a drawback also. Okay. But very simple solution to allow only one process in a critical region at a time is called a disabling interrupt. Okay. Now what will happen here? Each process which is executing the critical region will disable all the interrupt just after entering inside the critical region. Okay. It will enter inside the critical region by disabling all the interrupts. Then that means that particular process is inside the critical region. That means it is executing the shareable resource. No other process can interrupt it, can create interrupt. Okay, it will disable all the interrupt. Okay, it will disable all the interrupt. And after used, that means before leaving from the critical region, it will re-enable all the interrupts. It will re-enable all the interrupts. That means when that particular process, which is there in a critical region, will not be disturbed by any other processes. Okay. Even when other process wants to initiate, wants to use the critical region, they can't even keep request. They can't even put request. Entering inside the critical region is not possible here after enabled the interrupt, after disabled the interrupt. But the other processes which could not even keep the request to use the critical region. Okay. This approach is really not good. It is not unwise actually, because user processes to give the power to turn off the interrupt is not actually good. Okay. Suppose the process did not turn on, that means did not re-enable the disabled interrupts. What will happen? The complete system will stuck. It will not, nobody can continue the execution. Okay. So this is not the appropriate way. That is one reason. What is the one reason? What is the limitation of this? Giving the charge of changing that means disable and enabling the interrupts to the user process is not advisable. Okay. Because user process should not access the resources directly. That's why we have the operating system. No. But now here directly we are giving the privilege. We are giving the privilege to enable and disable all the interrupt to a process is not good. Okay, what will happen? If it does not turn on the interrupt again after it executed the critical region, what will happen? Nobody can proceed. None of the process can proceed the execution. Okay, so that is a one disadvantage. Another disadvantage, if processor is a core processor, or assume that more than one number of processors, CPU, are there in the system. Now this will disabling the interrupt will disable only one CPU's interrupt. Okay. Then what will happen? Other CPUs processors can enter inside the critical region. Okay, so this is the two reasons. These are the two reasons we are saying that disabling interrupt is not the good idea to make only one process to use the critical region. Okay, there are two disadvantages. Please note down. If you read your book, you will not understand. Okay, so you have to note down how you understood. That way you have to note down. Then only later when you refer, it would be very easy for you. Okay, there are two advantages in disabling interrupt. That is the first technique to achieve impose the mutual exclusion. Okay. The first one is disabling interrupt, giving the charge to disable and enable the interrupt, complete interrupt on the hand of the process is not a good idea. Okay. Because intentionally the process can corrupt the devices, or if it does not enable the interrupt after using the critical region, then that will lead to issue. Okay, this is one reason. Then the another reason is in multi-processing system, this technique will not work only. Okay, there are multiple processors or there are multiple cores, whatever it is. This disabling interrupt will be applicable to only one processor. Okay. So then other processors will interfere in the critical region. So there is no use of implementing this in a multi-processor where the multiple processors are there in that system. You can't use this disabling interrupt to achieve the mutual exclusion. Okay. Next is called lock variables. Okay, next technique is called lock variables. Lock variables also, that is a second, this is a step-by-step invention. Okay, first they found disabling interrupt as a solution for mutual exclusion, to implement the mutual exclusion, and then that has many disadvantages. Then they went to lock variables. Okay, so second attempt is what? Lock variables. That is a software solution. Okay. There is a shared variable. Okay, there is a variable. Okay, there is a single variable you can call that as that variable as a shared variable. Okay, some variable, that variable can be shared by more than one number of processes. That is called a shared variable. Okay, initially the shared variable value will be 0. If it is variable, you can initiate the value, no? So you are giving the initial value as 0. Okay, so the shared variable is initialized by 0. When a process, any process, wants to enter, yes, okay, any process wants to enter inside the critical region, first it has to test the variable, that shared variable. If the shared variable value is 0, that denotes nobody is currently using the critical region. So the process set that variable into 1 and then it will enter the critical region. Okay. If the lock is already 1, what does it mean? Already somebody is in the critical region. So the process just, it has to wait until it becomes 0, until the shared variable becomes 0. Okay. So here 0 means that no process is in the critical region, and 1 means there is a process inside the critical region. Okay. So whichever process is using the critical region, by seeing the value of the variable is 0, that has to reset the variable. For example, currently that shared variable value is 0. Okay, it is seeing that, okay, it is variable is 0. Okay. So it will reset the variable to 1 and then it will enter inside the critical region. Why it is doing this? Then only when that process is inside the critical region, when other processes seeing that variable, it will be shown 1. Okay. So other processes will understand that, okay, somebody is there in the critical region. Okay. So like that, single variable, that variable is called a lock variable. Okay. So using the lock variable, we can achieve the mutual exclusion. This is the second algorithm. Okay. But the disadvantage of this algorithm has actually fatal flaw. But this disadvantage, which I'm going to say, no, that is very rarely happen. Okay. Sometimes it may not happen. Okay. But anyway, it is a disadvantage. Okay. What is that disadvantage? Before a particular variable, for example, one variable is seeing one process is seeing the variable, lock variable. Okay. I can say lock variable or shared variable also. Okay. Assume that lock variable. Okay. A process is seeing the lock variable value 0. Okay. Then the process is taking steps to reset it, because by seeing 0, it will know that, okay, nobody is there in the critical region. So it will try to reset. Assume that at the same time, it is multi-processing system. No, assume that in the same time, some other process is seeing that variable is also 0, and it is resetting it to 1, and it entered inside the critical region also. Okay. Now what is our first process is doing? Now process 2 is inside the critical region, but process 1 initiated, process 1 read, it already read that variable is 0. Okay. So then what it will do? It will reset the variable to 0, because already it is 1, no? It will reset to 0. And then it will enter inside the critical region. Now what? 2 different processes are there in the critical region. Okay. So that is the disadvantage here. Okay. I repeat, lock variables. Lock variable algorithm is nothing but there will be a single variable which is a shareable variable. Okay. Shareable variable. That variable can be shared by more than one number of processes. That's why I'm calling this variable as a shareable variable. Okay. So that variable, assume that variable name is lock. Okay. By default, when the system starts enter inside the multi-processing system, its value will be set to 0. So initial value is 0. Assume that there is a process created, it wants to use the critical region, it is seeing the variable, it is 0, lock variable 0. So it will know that, okay, the lock variable is 0. Nobody is there in the critical region. So it will reset the variable 0 to 1 and it will enter inside the critical region. Okay. Now currently that process is inside the critical region. What is the value of the lock variable? Lock variable value is now currently 1. Okay. Now there are other processes which attempt to use the enter inside the critical region. First, it has to see the variable lock variable, but lock variable value is 1, so it has to wait. It cannot enter inside the critical region until the current process which is there inside the critical region to reset the variable to 0. Okay. Now, what is our process which is there inside the critical region? It executed all the statements in the critical region. Now it is coming out of the critical region. It will reset the variable from 1 to 0. So now currently lock variable value is 0. Now the process which attempted to use the critical region will start to reset the value of the variable to enter inside the critical region. But here there is a possibility when one process is trying to reset the value. That means a process saw the variable value 0. So it will take it that no process is there in the critical region. So it is taking some time to reset the variable from 0 to 1. By the time some other process, the process speed may vary depending on its execution. Okay. So assume that there is a speeder process. It is seeing the variable. Still the variable is 0. It is quickly what it is doing. It is resetting the variable value to 1 and it enter inside the critical region. Now process 2 is there inside the critical region. Whatever process 1 is doing, process 1 already it read the value of the lock variable. It is 0. Okay. So it will reset it and then it will enter inside the critical region. Now there are two processes which are there inside the critical region. But how we can achieve the mutual exclusion, keeping only one variable, keeping only one process inside the critical region at a time only, we can achieve the mutual exclusion. That fails here. Okay. So this is lock variable. Next technique is called strict alteration technique. Okay, to understand the strict alteration technique, we need algorithm. Very simple algorithm, but this will vary process to process. Okay, algorithm will vary process to slight variation only, single line variation only, but anyway, it will vary. Okay. Now, what is this algorithm, strict alteration? Wait, I will share another screen. Because roughly, no, I just gave the values, then you can understand once again. Strict alteration. This is a screen. But just very roughly, I have written. Okay. So you just ignore the way I have written. This is just to understand. Okay. This is just to understand. I can't rotate. Can't rotate this. I can maximize, but I can't rotate. Let it be. 1 second, I just resize the window because I have to open the PPT. My God, PPT and also that rough workout.
Amma, can I just for only 5 minutes, please? Amma?
Okay. I should share the entire window. Students, what are you seeing on my window? Any one of you? There are two windows. Can you see?
Yes, ma'am. Yes. Photos and PPT.
But
Yes,
I don't know. This is just I scribbled. Chalo. So there are. Let me maximize. Okay. Now it is little better. So strict alteration. This is non-CS means not non-critical section. Okay. And then there is some statement. Observe in the while loop, here I terminated. You know the syntax for the while loop. While, and this is the predicate portion of that while loop. That means condition, okay, usually. But within the curly braces, opening and closing curly braces, usually you will have one or more statements. Okay, that is the actual syntax format of the while loop. But here, I put a semicolon here. That means I'm terminating the while loop here itself. I did not execute anything. Please understand. I did not execute anything. Okay, when I put this semicolon, what will happen? When condition is true, when this condition is true, what will happen in the while loop usually? The body of the while loop will be executed. But either the body nahi hai while loop ke liye. I terminated here itself. The second line is another statement. Okay, that is not the while loop ka statement. Okay. So now this is what they mentioned there as a busy wait. Busy wait. This is the logic using software. I can keep on execute the same same condition until I am getting a particular expected value. Okay. Please listen. What will happen now when this condition is true? The body part of the while loop should be executed, no? But here, when the condition is true, again it will check whether the condition is true. Again, it will check, keep on checking. That is called, we can say that is a spin loop also, spin, S-P-I-N, spin loop. Or we can call here as here we are using this as a lock. So we can call this as a spin lock, busy wait, all denote same. Okay, busy wait, B-U-S-Y, busy wait, W-A-I-T, wait. Keep on, it is what? Checking the same condition, but anyway, the value will be same only, no? So keep on, it will check. Test the condition, whether the condition is true. Again, anyway, the condition will be true. Again, the condition is true. Yes, again, the condition is true. Yes, again, like that. When this condition turns false, then only it will come to the next line. Okay. When the condition will be false, that will be controlled by another section of the code. You see the logic, you will wonder. Okay. So now assume that there is a critical region. Look at the diagram. There is a critical region. PA, process A, process B. Both the process wants to use this critical region. Okay. PA, PB. Okay. Assume that here turn, this is a variable. Turn is a variable. Turn not equal to I. I is a variable, turn is a variable. Okay. Now this turn variable is nothing but the ID of the process. We saw already in a process creation, whenever a process is created, it will be created along with its unique process ID. Isn't it? So every process, what is unique for each and every process? Its process ID is unique. Okay. Every student, what is unique? Your roll number is unique. Your name is unique? No. There can be more than one Abhishek in the class. Can be, no. So it can be repeated, name can be repeated, but the ID, whenever we are calling something as ID, it should be unique. Okay. So for you, how the roll number is unique, like that for process, process ID is unique. It will not be repeated. Okay, that means not repeated, matlab what? No more than one process will have same process ID. Okay, like how no more than one number of students will have same roll number. The same way here, no more than one number of process will have same process ID. Okay, but initially this algorithm, no, it was not implemented using the process ID, but there was a disadvantage there. That's why they just reframed this algorithm. So now we are seeing that algorithms which was reframed, okay, which was updated. Okay. Now turn variable, we are going to assume it is a process ID. It is integers, no? So some process ID, the process ID, which is trying, which is executing this code. This is a critical section. Okay. So the process which is executing this particular code, you know, that process ID. Okay, turn equal to process ID. So now you know process turn variable equal to process ID. Okay. Now, first we will take case one case. First, we are taking one case. Okay. Process A, assume that process A, first it is entering inside this code segment. Now, this code segment is a non-critical section. Non-critical section.
You're in mute. Hello, ma'am.
I muted, right? Okay, I am explaining by muting. Okay. Okay. Huh. So assume that there are two processes PA, PB wants to use the critical section. Okay. Initially assume that process A is executing this. Currently the process A is in currently in non-critical section. Okay. It wants to enter, if it has to enter inside this critical section. The critical section, I have given only critical section. What code is inside is not required now. Okay. We have to understand the algorithm. Whatever it is, some code segment will be there in the critical section that it wants to execute, who process A. Okay. So if it wants to enter inside the critical section, it has to execute this. It has to execute this statement. Okay. So process A is now executing while turn not equal to I. Okay. What is turn not equal to I? Turn is not the process ID. Okay. Turn, actually we assumed turn is nothing but process ID, no. Okay. So the turn, we assume that here only two processes are there, no. So first process ka process ID is I, second process ka process ID is J, like that we assumed. Okay, some process ID. Okay, but that should be unique. Okay. Now turn not equal to I. Look at here. We are assuming here. Both the cases we have to take and assume. Okay. So first we are in the first case we are assuming turn not equal to I is what? True. That means this is not the process ID of that process. Okay. Turn not equal to I. Turn not equal to I is true. See, that's what here I have given. Assume. You are assuming here it is true. Okay. Next you will assume it is false. Okay. So you are assuming turn not equal to I is what? True. Okay. So if it is true, then the condition fails. Yes or no? The condition fails. Because condition is what? Turn not equal to I. But here turn not equal to I is what? True. So when it is true, now what will happen? This condition is true. What will happen? Again, the busy wait. Again, it will check whether this condition is true. Then again, it will check the condition is true. Okay. Now, process A is there in a busy wait. Process A, where it is there in a busy wait. Where it is, the condition is true. So it is again and again, it is checking that the condition is true or what not. Okay. Till the condition become false, no, it will be like that only. It will be in busy loop only. Busy wait only. We can call busy loop also. Okay. Remember now process A is in busy wait. Now assume that process B comes. Okay. Process B comes. Process B is starting to execute it. Now process B is in non-critical section. It wants to enter inside the critical section. So it has to execute this code. Okay. Now assume that turn is actually now the process ID is process ID of what? Process ID of PB, assume. Okay. So while turn not equal to I is false now because it is equal to J. Okay. So turn not equal to, not this togetherly called not equal to. Okay. Turn not equal to J is false, which means turn is equal to J. Okay. Which means it is a proper process ID. Okay. Now, if the condition falls, as I said, the process B will enter inside the critical region. Okay. Now, process B is inside the critical region. Where is our process A? Process A is there in busy wait. Okay. Now, process B is in critical region. It will execute the critical region. After completing the execution of the critical region, it will execute turn equal to I. That means it will set the PID equal to PID of the next another process. Okay, turn equal to I. The moment the process B set turn equal to I, here the busy wait will be released. Isn't it? Now turn equal to I, no? So the condition false. Okay, the condition true, then only busy wait. Now the condition false. Who made this condition false? Another process which successfully execute the critical region and it made the turn equal to I. The moment the process PB changed the turn equal to I, here the busy wait will be released. The condition will be false. The process A will come inside the critical region. And then it will, after completing the execution of the critical region, it will set turn equal to J. Okay. here, what you have to understand? There are two processes wants to use the critical region. Turn equal to process ID, which could be I or J. Okay, we assume that it can be I or J. Why I or J? Because we assumed there are only two processes. Okay. Now assume that PA is starting it is first attempting to enter inside the critical region. Okay. So this is the code for the process A. So it is now currently in non-critical region, and then it will execute to enter inside the critical region. It will execute this while loop. Now currently the while loop is true. We assumed, this is assumption. Okay, the while loop is true. When while loop is true, now process A is there in a busy wait. It could not enter inside the critical region. It is currently in busy wait. Okay. Why it is busy wait? It is in busy wait because there is some other process inside the critical region. Okay. So now assume that a process B, that's what here I gave, process A till this, now it is in busy wait. Process B will execute this statement. We assumed that now process B, the turn equal to J, so the condition will be false, so it will come to the critical region. Now currently, the condition false, process is in critical section. Okay. Upon executing the critical section successfully, it will change the turn variable to I. Okay, turn equal to I. Once it changed to turn equal to I, here what will happen? Process A will come out of the busy wait loop because the condition will be false. Okay, because turn equal to I, here it is turn not equal to I. So the condition will be false. Once the condition false, the busy wait loop will be released. The process A will come inside the critical region. Now only one process is there in a critical region, which is process A. Upon executing the critical region, what the process A will do, it will set the turn variable to J. Okay. So like this, if even simultaneously both the process started also, the process which is actually having the proper priority, that will only be allowed to enter inside the critical region first. And the waiting process should wait till it reset the turn variable to its process ID, to other process ID. Okay. So this is the algorithm. So the algorithm will work like this. Okay. Okay. So next methods we will see in the next lecture. Peterson solution and the TSL instruction. This we will see in the next lecture. Okay. Now all of you can leave. Thank you. Thank you.
Hello, ma'am.
Yes.
Ma'am, yesterday there was a circular at our college site that our exams will start from 18th April in offline.
Yes, that was discussed yesterday in yesterday's meeting. They decided, students, this is decided already. Before April 30, all the first year theory examination should be completed. So if we want to complete to 30th, then at least we have to start 18 or 20, no, 20th of April. Okay. So by seeing the other circular, you don't think that your theory examination will be there in the month of May. That is non-autonomous colleges. Okay. Our college decided that the theory examination should be completed. That means all the papers should be completed before 30th April. Okay. And your practical will be conducted after that. So your practical will be there in May. Okay, so this was a decision made, but mostly no change will be there in this. Okay.
And ma'am, circular says that it would be in offline mode.
That was also discussed. That already I said, yours will be there in offline only, both practical and this. And another one they were discussing.